Okay, so this is the last lecture in this semester. So today we are just talk about the selected topics in computer vision field. So today I will just briefly introduce some application in computer vision field. So I think that you can understand all of the things within these 2 hours, right? So you can just enjoy the to understand what happened in the computer vision field recently. Okay, so as you know, we have a take-home exam, right? So we will take a take-home exam in June 22 from 2 p.m. to midnight, right? So I suggest you preserve the with at least 2 hours to take this exam, right? And as you know, this is the online exam, so you can download the midterm problem set, no, final problem set in Blackboard, and you have to or you must submit your answer in Blackboard again, right? So the scope of this take-home exam will from the lecture 1 through the lecture 13, the today's lecture. And yeah, and there is one more notification. So we have a final project presentation and report, right? So in this semester, we proposed several kinds of the project proposal in midterm, right? So most of you send an email about your project, and I gave you some comment, right? So following my comment or the other intuition, you can improve your method or the finish your project, and then you have to submit the project slide and video in maximum 5 minutes, but through my email, right? So it is the usual as midterm, right? Moreover, you have to submit the report as well in the final presentation. So report should be 1 or 2 pages that contain the project, your final project. It should contain the introduction, related works, proposed method, experimental result, conclusion, or further work, but not limited. So please prepare the final project presentation. The presentation due date is the June 26th midnight. Okay, so this is the 2 notification. Okay, so if you have any question about those kind of things, please let me know. Then I will give you some further comment, right? Okay, so yeah, one more thing. This is our final grading policy. So in this semester, we had 2 things. First one is the course project, right? We already submitted the project proposal report and presentation, right? Actually, project proposal report was just a slide. Right? And presentation was a video, right? And you have to submit the final project presentation again and the project report through my email. So you will, yeah, you're 35%. And our final exam, take-home exam, will have the 50 percentage among the whole our final grade policy. And there is one more thing, the class participation. Actually, it's a subjective measure, right? So yeah, this is our final grading policy. Okay. So let's start our last lecture. So today I will just briefly introduce the computer vision field. Actually, as you know, I was working in the computer vision field, but as you know, after deep learning, the border between the computer vision or natural language processing or the data mining or other things vague. It means that the several kinds of technique in the computer vision field can be used in many other applications, or other technique in other application can be also used to computer vision field. So now we are living in the deep learning world. So okay, let's just briefly introduce the selective topics in the computer vision field. So actually today I prepared so many slides, at least 30 pages, right? So you might not understand everything, right? Because to teach the computer vision technique, it takes about one semester or 2 semesters, right? But in this in this lecture, I hope you just enjoy the computer vision topics and try to understand what happens in the computer vision field these days, right? Okay, so let's start. So first of all, what is computer vision? So the computer vision is the science and technology of the machine that see and understand. So as you can see here, if we have the image something like this, as a human like us, to understand, there is the car, there is the traffic sign here, right? And there is the people, right? There is two people, and they have different clothes, right? And there is one more car. The 3D structure of the car is something like this, right? But as a machine, it's really hard to understand this image like us, right? So the goal of the computer vision is to make the machine that see and understand like people, like us, right? So to this end, there are so many applications or so many research fields in the computer vision field. Okay, so let's start. So first of all, I start with the local feature detection and local description. So what does it mean? So as you can see here, there's two images. So this is the query image, and this is the reference image. What we want to do is to find out the mapping field between these pixels and this pixel, and then this pixel should be matched to this pixel, right? This pixel should be matched to this pixel, right? So how can I do that? How can I do that? Generally, there are two steps. First step is extract the local patches, like here, and like this, and like this, and like this. This is the feature detection step. And then we can describe these patches like a vector or the descriptor. So then we can also describe the patches on the reference image like this, right? So like this, and then we can compare this feature descriptor to the like this, right? So we can just measure the similarity. Okay, let's say this is pixel I and this is J, this is L. Then we can measure the similarity between pixel I and pixel J based on this feature descriptor, and feature I and feature L, something like this. And then we can just pick the matched patches for each pixel, right? So this is the local feature detection and descriptor. As you can see here, to describe each patches as a feature descriptor, we can use the machine learning technique or the deep learning technique. because if you remember our previous lectures, we can describe the image or the patches or the signal by using the deep neural network. So we can also use the feature of this deep neural network, right? So as you can see here, this is a very recent paper published in CBPR last year. So by using the deep neural network, we can find the picture correspondence between pixels, something like this, something like this. Even though, okay, there are some there are some distortion among the under the illumination variation, or some blur here, but by using the deep learning based method, we can estimate the reliable correspondence field, something like this, right? So this is very popular field in the computer vision application. Another application is stereo matching. So in stereo matching, the objective of stereo matching is to estimate the depth information. What is the depth information? Something like this. It's relevant to the relative depth. Okay, so as you can see here, this object is closer to us than this one, right? So it means that this depth value should be larger than this one, or comparing to the background, the depth information here should be larger than background field, right? So this is the depth information. By using the depth information, we can reconstruct the image, something like this, right? So as you know, the object, the real world object, defined in the 3D space, right? Something like this. But when we take the image by using the camera or other things, it is projected to the 2D space, right? So stereo matching or the depth estimation is to reconstruct the 3D image from the 2D images. So how can I do that? So in stereo matching, we use the two images, the left images and right images. So, okay, so there is a stereo camera that has the two camera, left camera and right camera. It is similar to the eyes of the human, right? And by using these two images, we can measure the similarity between this pixel and measure the disparity between left and right images. So as you can see here, if the object is closer to us, the disparity is much smaller than the background part, right? So you can just imagine, right? And by using this information, we can estimate the disparity map. Then by using this disparity map or depth map, we can reconstruct the image by using this left color values, right? So this is the stereo matching or the stereo matching based depth estimation. So as you can see here, there's the left image and right image. This is the reconstructed left depth map, and this is the right depth map. And here is another example. This is left image and right image. As you can see here, these two images look similar, but there are some disparity difference. As you can see here, this part and this part, right? There are some difference according to the depth information, right? So the goal of the stereo matching is to estimate the depth information from the left and right image, like this. And by using the outdoor images in the ADAS, we can also estimate the depth information, like this. So as you can see here, by using the depth information, we can expect those car depths of those cars like this, and depth of this car, it looks like this, right? So it can be used in many applications, especially in the ADAS system. And there is another way to find out the depth information, especially photometric stereo. Comparing to the stereo matching, then use the two camera. In stereo matching, we just use the one camera, but use the different illumination. So as you can see here, this 3D object can be projected to the 2D space according to the different illumination, something like this, and this. So as you can see here, according to the depth information, there are some illumination variation. There are some appearance variation. So it means that by analyzing the appearance variation between this one, or this one and this one and this one, we can reconstruct the 3D information of this image, of this object. In other words, if we have this kind of the 2D images, we can reconstruct the 3D information from these 2D images. So this is a photometric stereo. As you can see here, this is the same object. I don't know what it is, but yeah, it's just like castle, right? So we have the fixed camera. We have the fixed camera and take the images as varying the time. Then we can get the several images with the different illumination condition, right? Then by using the every images for this same for this fixed object, then we can reconstruct images. We can reconstruct the 3D information, something like this, right? So actually, this is the ground truth. So comparing to the ground truth 3D information, we can find out the 3D information pretty well, right? So this is a photometric stereo. And there is one more technique to estimate the depth information. That is called the multi-view stereo things. Multi-view stereo. Then how can I do that? Comparing to the stereo matching that only use the 2-view images, in stereo matching, in multi-view stereo matching, we use the several kinds of the images taken under the different viewpoint with the different peoples, right? So if you imagine the Colosseum object, this is the camera, right? Camera, and so many people take a Colosseum in different viewpoint, right? With a different camera. So this is the output of the camera. Then what do you want to do? By analyze these multiple images, we want to reconstruct this 3D object. Then how can you do that? Actually, this is similar to the star matching. As you can see here, we can just find out the correspondence between images, something like this, something like this, something like this, something like this. And then this is correspondence. And then by using this correspondence information, we can estimate the depth information. Right? This is called the MVS, or multi-view stereo matching. So by using this technique, we can reconstruct the real world. As you can see here, this is the indoor reconstruction result. As you can see here, the quality of the reconstructed images are very high, and this is the outdoor reconstruction. Outdoor reconstruction. So actually, this is the loam, actually there was a paper, name was the building a room in one day, right? So in this paper, they tried to build the loam by using the so many images. So they just reconstruct the Colosseum, something like this, or other landmark by only using the computer vision technique. So this is very intuitive and interesting application. So by using this reconstruct the information, we can use in many applications, something like robotics or AR, VR, or what else? Something like the smart drone things. Yeah, you can use any application in by using the 3D information. So this is the multi-view stereo matching. And recently there is a very interesting technique just called the monocular depth estimation, or 2D or 3D information. 2D to 3D information. Actually, to estimate the depth information like this, we need the depth Q. For example, in this case, the depth Q was the multiple images. In this case, it was the different illumination. In this case, it was the 2-view images. But recently, by using the deep neural network, by using some neural network with the transfer learning technique, many papers proposed the way to estimate the 3D information from the single to the image, So as a human like us, this algorithm, this technique, this CNN technique import the depth information from only single image like this, or from this single image they estimate the depth information like this, right? So this is the reconstruct the 3D field. This is the 3D field, right? So this is a very interesting paper because comparing to the previous one, by only using the single, actually we already have so many single image, right? So it means that by using this technique, we can reconstruct the 3D information from every our single image, right? So this is very interesting further direction, but the quality of the depth estimation are not so great comparing to this multiple stereo matching, but there are so many progress on this field. But I guess in near future we can extract the 3D information from the only single our image using the deep neural network very accurately. Okay, so this is the monocular depth estimation, and another application is the optical flow. Okay, optical flow. So goal of the optical flow is to estimate the motion information. So this is the image in the t-1, and this is the image at t frame. So this is the video. What you want to do is to estimate the motion information between two adjacent images. For example, as you can see here, this car moved to here, right? So this pixel will move to this one, right? So if we overlap these two images in here, the new car was something like this, and there are some movement between this pixel and next pixel, right? So by finding out the movement or the motion between t-1 image and t image, we can estimate the motion information on in the video, right? So this is the goal of the optical flow or the motion estimation. So as you can see here, this is the image by ADAS. ADAS. You know what it is? So ADAS means Advanced Driving Assistant System, like a Google driving car, right? So this is the image, right? This. So by using the optical flow algorithm, we can analyze the motion information on our images. And here's one more application, just called the tracking or the object tracking. Object tracking. What I want to do is to analyze the movement of the peoples or the object by increasing the timestamp. So actually there are so many images as varying the time, right? So by using the optical flow, we can track the object, right? Or in this, actually this is some CCTV taken in the fixed viewpoint. Then by using the tracking algorithm, we can track each human's trajectory, something like this, right? This. So to track these patches, we also use the correspondence between patches. So by using this technique, we can analyze the human's behavior or the other object's behavior, right? So this is the object tracking. And here's one more very interesting application, just called the semantic correspondence. So what is that? So from here, most this application based on the correspondence between two view images and the photometric stereo images, or the multiple viewpoint images, or the time similar images, something like this. Or yeah, this is also time similar images. But in semantic correspondence, the objective is to establish pixel level correspondence between semantically similar image. For example, as a human, we know that this is a car, right? This is car, but different car, right? But we know this part corresponded to this part that corresponded to this one, this part that corresponded to this one, right? So in other words, if we can find out the correspondence field between the two images that have the different data from the different instances within the same category, then we can solve so many applications in the computer vision field. So for example, the non-parametric or the example-based scene understanding. So what does it mean? Okay, so let's see. So this is the image in the Google or the Flickr or the Facebook, something like that. We have so many image data, right? Then here's our image. We want to analyze the label or depth or something like this, but we only have the single image, right? But in some image, in some nearest image, they already have some label, motion, depth information like this, right? Something like this, right? Then what I want to do is, if we can find out the semantic correspondence between these pixels and this pixel, or this pixel, we can extract the label, motion, depth information by by transferring to the input image or the query image by using the semantic correspondence, right? So by using this kind of thing, we can solve the non-parametric scene understanding problem using the nearest neighbor images. So this is the applications of the semantic correspondence. For example, I will briefly introduce the object detection, semantic segmentation, or key point annotation, part segmentation in the later slide. But in here, I will just briefly show the application by using the semantic correspondence. So by using the semantic correspondence, we can detect the object reliably, something like this, or segmenting the image according to their semantic label. For example, this is a human and this is the bike, or semantic key point. This is the same point across the different images. So this is the application of the semantic correspondence. And what else? By using the different instance images from the same object category, we can reconstruct the 3D information from the single view images. Or colorization. If we have the single gray image and we have the color image, then by finding the correspondence field, something like this, something like this, something like this, then we can find out the color per image from the gray image, right? So this is the colorization. We can solve the colorization problem by using the semantic correspondence. Other application is object code segmentation. If we have the image set, the set of image in the same class, in this case car, then in some application we want to segment the car consistently across the different instances like this, right? So this is the object code segmentation. So in this case, by using the semantic correspondence, we can solve the object code segmentation. Another application is something like this. Actually, this is the video. This is the video. This is the input image, and this is the input. This is the input mask, right? So by finding the correspondence between this image and the another frame images, or here and here, we can propagate this label, something like this, something like this. This is another application, semantic mask propagation, or pose propagation here, or text propagation, like this. So this is the video label propagation application. And what else? Another thing is that the human understanding or the human modeling. So by using the computer vision technique or the deep learning technique, we want to analyze the human face or the gesture or the body pose. Then by using those kinds of information, we can understand the human's behavior, right? So for example, if we use the face detection or the face identification, we can understand this human comparing to the other human's face. So we can use this technique for the face identification. Or as you can see here, if we have the image like this, then we can find out the human's body pose, something like this, or something like this, right? So those techniques also successfully applied by using the deep neural network or the convolutional neural network. So as you can see here, recently we can successfully find the reliable corresponding human mask or the human body part in the 3D domain. Actually, this part is defined the 3D domain. So as you can see here, yeah, the quality is really nice, right? So this is the another computer vision application. And as you can see here, if we have the image like this, right, or human image, then we want to find out the skeleton per each human pose, something like this, right? So by using this pose information, we can understand the human behavior, something like this. Okay, so from here we can imagine they play their basketball, maybe something like the human behavior. How can I say behavior? Anyway, so we can analyze the human behavior by using the deep neural network. And one more thing, this is the emotion recognition. To conversate with a human, the machine have to recognize the human's emotion. So can you imagine the her emotion or emotion of this person or this person. So to understand the emotion of this person, we first understand the face region, right? But simultaneously, we also have to analyze the gesture information or the interaction between other people, like this, or the another gesture here, right? So in this paper, by simultaneously use the face information here and the another context information, they estimate the emotion of the human by using the deep convolutional neural network. Yeah, so yeah, this is the another application. So yeah, so then I want to move to the recognition part. So before that, let's take a break.